Alright, welcome everybody. So today I wanted to talk to you a little bit about the Bohr model, and I wanted to review, how we got to where we are. So in class we've done a lot of review where we talked about, well, we started with Dalton's model, we went to Thomson, we went to Rutherford, and then we kind of took a detour in the notes where I started talking to you about the properties of light. And the reason why I wanted to do this was because what Bohr did in his model was he used this information, this idea that light is quantized, that you have these little wave packets of energy called photons. And he used this to explain how electrons could orbit the nucleus and how they could have these stable orbits. Remember that Rutherford's big problem, one of them was that the electrons should just be spiraling into the nucleus, and yet here we have the situation where the electrons are in stable orbits. So what did Bohr's model look like? And I know I said this last time, I want to go through it again with you. First of all, he said that the electrons can only have certain orbits, and these orbits have a certain amount of energy. The only way that an electron can move between orbits is if they absorb energy. So when the electron is in a permitted orbit, it'll have a specific amount of energy, and no energy will be emitted or absorbed by that electron. It's a stable orbit. The electron, though, can absorb a photon. That photon will have a specific amount of energy. You could calculate that energy of the photon, and you can do that by using E equals h times frequency. That electron will absorb that photon of energy, and it will cause the electron to jump into a higher orbit. Now the thing is that when the electron jumps into that higher orbit, and I show that over here on this side, let me just highlight this, here's my atom with my electron in a stable orbit. I show a photon being absorbed by that electron, and then I show the result. The result is to have the electron now in an excited state, they call it. This is the excited state. Originally, we would call this one that's highlighted the ground state. So the electron will move into an excited state. But this excited state, it's not stable, it's unstable. And so the result is that the electron will return back to the ground state, and it will release energy. Now, that energy is emitted by the electron, and the energy will have a specific wavelength, because the energy that is emitted as a photon. If we know the energy of the photon, we can calculate the color of the photon, and we can see that it has a specific color, and that corresponds to what's known as a line spectra. Now, what did Bohr's data actually look like? Well, this shows you down here what Bohr's data actually looked like. Instead of having some sort of continuous spectrum where the electron would just be spiraling into the nucleus, instead what we see is that there are unique individual lines that are created when the electron moves from the ground state to the excited and back to the ground state. And that's really important to understand. These different colors that we see here, each line, it represents an electron transitioning from a higher level to a lower level, and the color of the line is related to the energy that we see when we look at Planck's equation. Now there are some, pretty in-depth calculations that we could do to actually predict what the colors will be. And what Bohr saw was that the lines matched up perfectly to what he predicted. He predicted that the lines would have certain colors. For hydrogen, he was able to predict that exquisitely. So down here, I just want to summarize what we talked about. Here's an atom in the ground state, hydrogen, that's what he used. A nucleus with one electron. Here's my electron orbiting my nucleus, my photon will come in. So now the electron absorbs the photon's energy. This causes the electron to jump to a higher orbit. This is called the excited state. This is unstable, and so the electron will emit energy that corresponds to E equals h times frequency and return back to its ground state. This energy that is emitted, it has a specific color. Now it turns out that the atom and the electrons in it, the electrons can travel up to 7 different levels. And they don't have to go back down to the first level. They can go from the 5th level to the 2nd level, the 7th level to the 4th level. And I show that on the next slide here. What you can see is over here what I highlighted, and I'll just unhighlight it now and re-highlight it again. But what you'll see is that each of these energy levels, these orbits, the difference between the first and the second energy level, there's a huge energy gap between them. This corresponds to energy. So between 1 and 2, there is a huge energy gap. Between 2 and 3, there is a smaller gap. And then it gets smaller and smaller. Between 3 and 4, it's even smaller. Now, depending on how the electron moves will determine what type of light's given off. If the electron returns to the first level from any other level, that's the pink lines over here. That's these lines over here. You will give off ultraviolet light. That is more energetic because it's such a big energy difference. If you go back to the 2nd level, so the green arrows, you will give off visible light. If you notice, there's 4 green arrows here. If we scroll back for a second and you look at the hydrogen spectrum, what do you see here? We see 1, 2, 3, 4 lines. Each one of those lines corresponds to an electron moving back to the 2nd energy level. This series of lines has a name. It's called the Balmer series, B-A-L-M-E-R series. What's interesting is that scientists had seen these spectral lines, but nobody could explain what they meant. It wasn't until Bohr that they understood what was going on with the hydrogen atom. You see that throughout science, that with Planck, he knew that light was emitted as some kind of packet, but he couldn't understand quite what was going on, and it was Einstein who came in and finished the deal. And now we have Bohr coming in and explaining what Balmer and other scientists had done. So, if we want to show what the Bohr diagrams look like, we have a nucleus, and then around it we have our electrons. The first level, so this is n equals 1, the first level, this is the smallest. It can actually only hold 2 electrons. I want to discuss tomorrow why it can only hold 2 electrons based on its size. So let's talk about that tomorrow. The second level n equals 2, it can hold 8 electrons. So if we have n and we have the number of electrons, the first level can hold 2, the second level can hold 8. The third level can hold up to 18. and the fourth level can hold up to 32. There's a general formula that you can use. You can do number of electrons equals 2n squared. Now take, for example, if I had an atom like sodium. Sodium has a configuration 281. When we do electron configurations, we'll talk more about this. But when I look at this, if I were to draw this, I'd have my nucleus, I'd have my 2 electrons, I'd have my 8 electrons, and then I'd have my 1 electron out here. This would be the ground state. What I'd like you to do and think about is, what would this be if it was excited? So this is all of Bohr, and what we're going to do next time is we're going to talk about the quantum mechanical theory. It goes beyond what Bohr is saying, because what we figured out about Bohr was that although his model is useful, and we still use it today, and you still learn about it in 7th grade, this may seem familiar to you, it's not completely accurate. There's a model that's more complex, and it's called the quantum mechanical model or the orbital theory, and that truly describes how an electron is located in an atom. Why do we care so much about the electron configurations? Why is it so important? Why do we care about this for chemistry? Well, hopefully we can talk about that too. So draw me an excited state. Think about why we care about this. Go through and make sure you know the Bohr model well. Okay, thanks so much.